Bismillahirrahmanirrahim. Assalamu alaikum students. In last lectures, we were discussing the consequences of Einstein's postulates, consequences of Einstein's postulates. I continue that topic. I write continued. Remember, in last lectures under this heading, we discussed first the relativity of time, and we derived the equation delta t equal to delta t naught over under root 1 minus u square over c square, right? Situation was like this. We considered two reference frames. I'm just refreshing your memory, S and S prime. So S is at rest on the ground and S prime is in a train moving on a long straight track at constant speed u relative to S, right? What is delta t naught? We called it proper time. It is the interval measured by an observer, in our case S prime, relative to whom the clock is at rest, right? And delta t is the interval measured by the frame S, which is sitting on the ground at rest, right? And we said all observers in motion relative to clock measure longer intervals. The proper time interval between events is the smallest interval between them that any observer can measure, right? Then we discussed second thing, the relativity of length, right? And under this heading, we derived this equation L is equal to L naught under root 1 minus u square by c square. Let me name them in this lecture, this 1 and this 2. What's L naught? L naught is called rest length or proper length. It is the length measured by an observer, in our case S prime, who is at rest with respect to the object being measured, right? Now all observers in motion relative to S prime measure a shorter length. So our S observer measures length L, which is shorter than the proper length L naught, right? And we said the shortening of the length is only along the direction of motion. Length measurements transverse to the direction of motion are unaffected, right? And remember our timing machine. I'm just refreshing your memory in order to continue with my next topic. So we had a flash bulb and a detector, and we had a mirror M, This length we called L naught. This was our timing machine. So what is our tick? This flash bulb gives off light. That light travels to the mirror and comes back to the detector. Now, the time taken by this light in this round trip is our tick of the clock, right? When we discussed uh, the relativity of time, this clock was carried by S prime, and S prime was moving in this way at speed u, right? And we establish it this relation. Then, when we discuss the relativity of length, we shifted our time machine this way, where this mirror, same flash and detector, and this timing machine was going along the motion of S dash observer related to S observer. So this was motion. So in this situation second, that is the situation considered in relativity of length, the uh, light was traveling in the direction of motion of the train on which observer S prime was staying, right? Now we have to discuss next consequence of Einstein's postulates. Let us move forward. Now we have third consequence, the relativistic addition of velocities. Remember, we have already discussed the Galilean version of velocity transformation equation, but that equation allows a body to travel at a speed greater than speed of light. But the Einstein's postulate restricts. We have a speed limit c, so we have to modify the velocity addition relation. We will discuss that today. The how to add the velocities observed by two different frames, or how to relate the velocity of a particle observed by S and S prime, so that Einstein's postulates are obeyed, right? So let me draw the figure. In this figure, we modify our timing machine again to establish the relation. The situation is like this. You can draw the figure with me. Let me name it figure 1. What does this figure 1 show? Actually, we have modified our previous timing machine, this one. We have modified. What we have done to it? The flashing bulb F is moved to the mirror. So we have moved this flashing bulb F to the mirror M. There is no mirror now, right? And instead of flashing bulb, we have placed a device P. This device P emits particles at a speed V naught as measured by an observer at rest with respect to the device, right? So I repeat, P is a device that emits particles at a speed V naught as measured by an observer at rest with respect to the device. With respect to the device, right? Now this flash bulb, when struck by a particle, is triggered and it emits a light beam. That light beam makes the return trip to the detector, right? So our timing machine is now detector, particle emitter, and bulb flash. So particle emitter emits particles at speed V naught. They hit the flash bulb, they trigger it. When particle strikes the flash bulb, it emits light. Light travels back to the detector D. So now our tick is this one, round trip. But for first part of the trip, the time taken by the particle to reach the flash bulb is one part of the tick of the clock, and second part of the tick is the time taken by the light to move from flash bulb to the detector, right? And keep in mind that the particle emitter emits particles at speed V naught as measured by an observer at rest with respect to the device. In our case, that is the S prime observer, right? Now, uh, time interval delta T naught. Now, time interval delta T naught measured by an observer, measured by an observer such as S prime who is at rest, who is at rest with respect to the device, with respect to the device. Remember, this device is carried by the observer S prime, who is on a train moving at velocity u in this direction relative to observer S staying on the ground, right? So S prime is moving with the device relative to S. S is at ground, right? So the time interval delta t naught measured by an observer such as S prime who is at rest with respect to the device consists of two parts. Consists of two parts. One due to particle traveling distance L naught at speed V naught, and another due to light beam traveling the same distance at speed c. Therefore, let me use this color. Therefore, delta T naught is equal to L naught by V naught plus L naught by C. Let me name it equation third. What is L naught by V naught? It is time taken by the particle moving with speed V naught relative to S prime to reach the flash bulb, right? The L naught by C is time required by the light to move from the flash bulb to the detector. When you add these two times, you get the time interval measured by observer S prime. Now the sequence of events. The sequence of events observed by S as the timing device is carried by S prime on the train is identical with that of uh, the previous figure which we discussed in relativity of length. I will not make this one more time. Remember when we discussed the relativity of length, we showed this figure. We had this mirror here. Now we will have, instead of mirror, we will have flash bulb, and here you will have particle emitter, and here you have detector, right? It's moving with velocity u, and first part particle will start from this point. Then in second situation you can show this is my P. Let me clear it. This is my P, this is my detector, and you have a flash. In second situation you show particle reaching the flash bulb. Then in third situation you show particle emitter detector. Then you have this flash bulb. Then you show the particle this light here emitted by the flash, and here it reaches the detector. Compare it with the previous diagram. So here particle is emitted, then it reaches the flash, light is emitted, and here light reaches the detector. Whole arrangement is moving to the right at velocity u. Now, this is the sequence of events observed by S. Now the emitted particle which travels at speed v according to S, different speed. So I will not show this velocity as v naught. Let me clear it. This velocity is v now, not v naught. Why? Because the velocity measured by observer S will be different from the velocity measured by observer S prime. Remember, S is sitting on the ground, right? So the emitted particle which travels at a speed v, let me write it, the emitted particle which travels at speed v according to S reaches F after an interval delta t1 during which time it travels a distance v delta t1, right? Which is equal to the contracted length L plus the additional distance u delta t1 moved by the train in that interval. So I write v delta t1 is equal to L plus u delta t1. What is v delta t1? It is the delta t1 we said is the time required by the emitted particle to reach the flash bulb, right? And during that time, the particle, according to S, travels v delta t1 distance. So we said it is equal to L plus u delta t1, where L is the contracted length and u delta t1 is the distance traveled by the train in delta t1 time. So I name this equation. This is my 4. Now in the interval delta t2, now we talk of the second part of the interval. First part is the time taken by the particle to reach flash. Second part of the interval is time required by the light to move from flash bulb to the detector. So In the interval delta T2, the light beam travels a distance c delta T2. C is the speed of light, and this c delta T2 is equal to the length L less the distance u delta T2 moved forward by the train in that interval. That is C delta T2. It is easy to understand. You can check it. C delta T2 is L minus U delta T2. C delta T2 is the distance traveled by the light in time delta T2. L is the contracted length. U delta T2 is the distance traveled by the train in forward direction in interval delta T2. So I name it phi, right? Now what we do next, I will write directly, you will check that. So we solve 4 and 5. I write solving equations 4 and 5. That is, this is our 4, this is our 5. We have to solve them for delta T1 and delta T2. We can then find the total time interval delta T equal to delta T1 plus delta T2 between x according to S, right? And we substitute that result, and we substitute that result along with equation, what is this, what is the number, along with equation this one 3, along with equation 3 into equation which one, this one, this number, into equation 1, which gives I should specify after using equation, this one 2, using equation 2 to relate L naught and L. What do we get? We get V equal to V naught plus U over 1 plus V naught U by C square. What is its number? This is our required equation. I name it equation 6. Let me repeat it. What you do, you chuck it, this is your homework. Chuck it at home. So what you have to do, first you solve 4 and 5. This one and this one, right? For delta T1 and delta T2, right? Then you add total time interval, delta T1 and delta T2, you get delta T. The delta T is actually the time of tick according to observer S, right? And you substitute that result along with equation 3, this one for delta T naught, into equation 1. Which one? This one, which relates delta T and delta T naught, right? And you will get this after using equation 2 this one, which relates L and L naught. You chuck it at home. So you get this equation 6. V is equal to V naught plus U over 1 plus V naught U over C square. What is V? It is the velocity of the particle as measured by observer S. What is V naught? Velocity of the particle measured by observer S prime. U is the relative velocity of the observer S prime with respect to S. C is the speed of light. So this equation 6 gives one form of the velocity addition law consistent with Einstein's postulates. Here we are concerned only with adding velocities that are along the direction of relative motion, right? Now, according to Galileo and Newton, a projectile fired forward at speed v naught in a train that's moving at a speed u should have a speed v naught plus u relative to an observer on the ground. This clearly permits speeds in excess of c to be realized. The difference between the classical result and the relativistic result is the denominator of equation 6, right? So without this denominator, the result is classical. With this result, it is in accordance with Einstein's postulates, right? It is this denominator which forbids the measured speed of a particle, it forbids the speed to exceed c, right? So under ordinary circumstances, our denominator is close to 1, and this equation is just the classical result of v is equal to v naught plus u. So let us do a sample problem. So there's a question which says a spaceship is moving away from the Earth at a speed of 0.8 c when it fires a missile parallel to the direction of motion of the ship what would be the speed of the missile as measured by an observer on the Earth. I repeat the question before going to the solution. It says a spaceship is moving away from the Earth at a speed of 0.8 c when it fires a missile parallel to the direction of motion of the ship. The missile I have missed a portion. Let me write here. The missile moves at a speed of 0.6 c relative to the ship. Now question is complete. I repeat it, a spaceship is moving away from the Earth at a speed of 0.8 c when it fires a missile parallel to the direction of motion of the ship. The missile moves at a speed of 0.6 c relative to the ship. What would be the speed of the missile as measured by an observer on the Earth? So this problem is similar to that of the observer and the train. Here S prime is on the ship and S is on the Earth, and S prime moves with speed u. So u is 0.8 c. So S prime moves with speed u equal to 0.8 c relative to s. The missile moves at speed v naught equal to 0.6 c relative to s prime, and we seek its speed v relative to s. So using the relation we obtained just now, v is equal to v naught plus u over 1 plus v naught u by c square. Substitute all the values. I will write directly the result. It will give me 0.95 c, right? So the velocity of the missile as measured by an observer on the earth is 0.95 c, right? This is all for today. Go through all the video lectures. Don't waste your time, and don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.